Hello guys, so this is the first video of lecture 8 in which we're gonna continue our analysis but now using the constant voltage model for the diode. Okay, we explored the exponential model, the exact model, and we solved many examples, and now it is a turn for another simpler model, which is the constant voltage model. We explored already one example in the last video, the end of lecture 7. So I'm just to recap now what is the constant voltage model and just to continue solving examples using it. Okay, so basically we approximated the exponential IV characteristics, the curves, non-linearity, all such stuff to such a very easy, model. Okay, so basically we have forward and we have reverse. Okay, if the diode is forward biased, okay, then we have two possibilities. Either we are working in that region here, region 1, or region 2. In region 1, the current is 0. So one of the unknowns is known, which is the current. So basically, the analysis is to find VD. And VD should be greater than or equal to 0. This, again, a transition point cannot be expressed at forward or reverse. And less than or equal to 0.7. And the second region, okay, the current is greater than or equal to 0. And VD is constant, 0.7. Again, here, one of the unknowns is known, which is the voltage now. Okay, and it's all, the analysis will just is done to find ID. And when I say greater than 0, I mean it's positive, and of course greater than 0. And when I say greater than 0 and less than 0.7, again it's positive and in that range. Positive means when you assume the direction, the current should be flowing in that direction and positive, and the voltage should be in that direction and positive as well, in forward, whatever region 1 or region 2. Okay. In reverse, we also have two regions. We have this one. Let's do with another color. We have this region here. In which the current is 0 and the voltage is less than 0 and greater than V breakdown. Again, the transition points, this and this, you cannot say it's a transition point. It belongs to both regions. Okay. And you must find the current is voltage here negative. Negative means with that direction negative. If you find it positive, then your assumption is incorrect. And in forward, you find the voltage positive. If you find it negative or the current negative, then your assumption is also incorrect. The second region is the breakdown region, in which VD is constant equal to minus V breakdown. I usually express V breakdown with these two bars as an absolute, because some box you will find the value negative and some other box finds the value is positive. So they consider it as reverse. They can express it as positive, and when you locate it on the coordinates here, it should be in the negative region, which is confusing. So I just make have peace in my mind and just put the absolute, and whatever it is, I put the negative in front of it. And the current in breakdown region should be less than 0. Okay, I'm sorry. Should be as a magnitude should be greater than 0. As a value should be less than 0, less than or equal to 0, because again the transition point, the current is 0. Then the current will increase in the negative direction. Okay, and we can determine its value based on the circuit. and it should be negative. It must be negative. If it was positive, then you have some problem, or the assumption is incorrect. And basically here, if you are not sure, okay, we play the game of assumption. Assume something. If it's not correct, then assume some other stuff. And we have here basically 4 assumptions, you know. And for many problems, the breakdown voltage is pretty high. I mean, minus 1000, for example. So basically in the reverse, it's just open circuit and that's it. There is no breakdown. Okay, guys. So this is just a quick recap for the constant voltage model. So let's now take an example. So our example here is a diode circuit, which has 2 diodes, D1 and D2, okay? And a resistor here. And it's required to find the voltages and the current, okay? At 4 possible combinations of VA and VB. So VA and VB can have, VA and VB can have 2 values, 0 and 1. I'm sorry, 0 and 5 volt. 0 volt or 5 volt. So VA can be 0 or 5, VB can be 0 or 5. So all possible combinations is 0, 0, 0, 5, 5, 0, 5, 5, something like this. How we know the number of combinations here? It is 2, the number of variables, to the power of 2, which is the possible values that each variable can take. So each variable here can take either one of 2 variables, 0 or 5. Why it cannot be 1.5? This is the requirement. So basically here we are discussing a kind of application, but I will explain it at the end, which is the OR logic gate. But I will delay this to the end of this. I will just solve it as a circuit without touching any possible application for it, just as a circuit, okay? So this is I load here. This is ID1. This is ID2. This is VD1. This is VD2. So let's take the 4. It's like you will solve this circuit 4 times. That's it. Okay. Each time you take possible different combination for A and B. So number 1. And each time we're gonna find the output, you know, and fill this table here. So when VA equal to 0 and VB equal to 0. So first of all, just to imagine it, okay? So just to consider this, that this VA is just a battery like this. And VB is also a battery. And we can just, you know, it changes the battery with the battery is equal to 5 volt and the battery equal to 0. Okay, that's it. That or another good approximation for it to understand what is this 0 and 5. Just to consider here, like, oh no, it's yeah, yes. Just to consider if you have a kind of switch like this. And also a switch here. Okay. What happens if we close the switch? So let's call it SA and SB. If SA is closed, VA will be 0, right? Because we shorted the battery. If SA is open, VA is equal to 5. And same for SB, the switch at B. If this switch is closed, VB will be, this battery will be shorted. So VB will be connected to ground. So VB will be equal to 0. If SB is open, the switch SB is open, then VB will be just the battery voltage, which is 5 volt. This is how we understand what I mean by putting a voltage at some node in the circuit. Okay, good. So let's go back to our favorite color here. Okay, good. Now just look at the circuit. Okay, with 0 here and 0 here. And remember, you have a ground. This is 0 as well. As a voltage, it's 0. Okay. For the diode to conduct, okay, it needs a source, right? Here, there is no source. Here, it's something like this. Like if I'm giving you a circuit like this with no source, and I'm asking you what is the current ID. There is no source, right? Either current source or voltage source. To generate a current, we must have a voltage difference that comes from a source, of course. Either current source or voltage source. Even the current source has a voltage difference, but it's unknown. We know the result, we know the current, but we don't know. We should determine it from the circuit. Okay, so basically with VA and VB equal to 0, okay, there is no current, so there is no source. So ID1 equal to ID2 equal to 0. So IL will be equal to 0 as well. So VL, which is the voltage across the resistor here, or V output, one of our unknowns, is equal to IL times RL, so equal to 0 as well. Okay. So in that case here, we determine the output. It's equal to 0. Let's now solve number 2. Now in 2, VA is 0, but VB now is 5. So let's do it in another color, green for example. So now VA is still 0, but VB now is 5. What does that mean? That let's go to the switch example. So that means this one is, this switch is closed. So A is connected to 0, but SB is open. Okay, so VB is equal to 5. So now we have 0 here and 5 here. Okay. So based on that, let's check now. D1, the B terminal of D1 is close to a 0 voltage. It's connected basically to a 0 voltage. And it's in, it's also close to the ground here. And remember, for a diode to be in forward, let alone to take 0.7, okay, its B should be greater than its N by 0.7, so that it can conduct according to the constant voltage model. So basically here VA can be assumed off. But we don't know if it's reverse or forward, but the voltage is less than 0.7. We're gonna see. We're gonna solve the circuit and see. But it's off. But look now at DB. at D2 or D2. D2, its B is connected to the highest voltage in the circuit, but N is near the ground. So looks like B is on, forward and on. One may say this looks like, you know, sloppy or will be based on luck. No, after that guess that it will show that now it's correct. I will assume with you the incorrect assumptions, and we will see that this incorrect assumption will lead to some inconsistent result. Okay, so let's continue on that. If dA is off, then IA or IDA for sure is equal to 0, or ID1, because we can name this as DA and DB. It will be much better for us. Okay, it's much better than naming them as DA, as D1 and D2. So this is IDA, this is IDB, this is VDA and VDB. And if DB is on, then VDB is 0.7 volt. If DB is 0.7 volt, that means, remember, VDB equal to the voltage of the B, which is VB, minus the voltage of the N side, which is VO or V out. This is the voltage difference. The voltage difference of any diode, the voltage of the B side minus the voltage of the N side. The voltage of the B side is connected to VB. The voltage of the N side is connected to V out. VDB, based on our assumption, is 0.7. VB, based on our assumption, is, based on the givens here, is 5 volt. And V out is unknown for us. So from that equation here, V out equal to 5 minus 0.7, which is 4.3 volt. Now is a moment of truth. We assumed that DA, diode A, is off, right? Let's check that. Let's check that. So what is now VDB or VDA? VDA is the voltage of the diode A, which is VA here, minus this point, the N voltage, the N side voltage, which is V out. VA is 0. In number 2, case 2 here, VA is 0. And the V out, we just get it, it's 4.3 volt. So based on that, we can see clearly that VDA is minus 4.3 volt. So it was reverse. It was reverse. Because the voltage of the N is greater than the voltage of the B. This is really clear. We don't need even to calculate VDA. Because here, look, the B side is connected to 0. The N side is connected to 4.3 volt. So the voltage difference is negative. It's reverse. So that's our check. Now we proved that our assumption is correct. Now let's have an insight. Let's do it in another color. Okay. So we just finished now, number 2, and we discovered that V out is 4.3 volt. So in number 8 was 0 volt. In number B, or in this one, it is 4.3 volt. Now before we go to number 3, I will just make you very sure about our process here. Let's assume that DA was on. which is incorrect, of course, but let's assume so and see what's gonna happen. So let's do that in black. So just to be, 1,000 or 100,000 or 10,000% sure, let's assume DA on, just like diode B. If DA is on and DB is on as well, if DA is on, then VDA is 0.7, which is equal to VA minus V out. Just look at the terminals here. VDA equal to this point minus this point. VA minus V out. So 0.7 equal to VA is 0 and V out is unknown. So from here, V out equal to minus 0.7. Okay, no problem. So the B side is 0 voltage, the N side is minus 0.7. So yeah, there is a voltage difference to the B side. I mean, the B side is bigger than the N side by 0.7. Since we assume that DB is on, so VDB is also 0.7, which is equal to VB minus V out. So we can determine V out from here also. So from here, 0.7 equal to VB, remember now is 5 minus V out. So from this one, V out is equal to 4.3. So which is correct? Now you have a contradiction. From one branch, VB or V out is minus 0.7. From another branch, it's 4.3. So we have a contradiction, right? So this assumption, which is DA on and DB on, is incorrect. Now you are, 10,000% sure. Okay, although of course, just until this point, this is our solution and that's it. Okay, you don't need to do that each time. I'm just doing it with you just to make you, more sure. Now let's go to the third case. VA 5, VB is 0. So let's do this with another color. So we tried blue, we tried green. Let's do with this, light blue. So number 3. VA 5, VB 0. Just look at this circuit here. If we draw it in that way, and call this VB and call this VA, and this is DB, DA. I mean, we just changed the order. This was top, it become now bottom. I mean, DB or DA, and DB was bottom, it become up. Does this change the circuit? No. So basically, we already solved this case. When we solved VA equal to 0 and the VB is equal to 5, you just change what's happening. I mean, if at VA equal 0 and the VB equal 5, DA was off and DB was on. Now in that case here, DA is on and DB is off. Okay, and this will be the correct one. You just switch everything. Let's calculate V out. So since DA is on, so VDA is 0.7 equal to VA minus V out. So from here, V out is equal to VA, which is 5 minus 0.7. It will be 4.3. Now let's check that VB is really off. If we calculate VDB, it will be VB minus V out, which is 0 minus 4.3. It's minus 4.3. It's reverse. We just switched positions. So when VA was 0, VB was 5, DA was reversed, and DB, diode B, was forward. Now, with VA equal to 5 and VB is equal to 0, we just switched. So DA become forward, DB become reverse. And the final conclusion is that we have here 4.3 volt. Let's now do number 4 here. The force. Let's again change the color. Let's do with black. Or is that orange here? So number 4. VA 5, VB 5. Before we assume anything, just look at what we have. You will notice something in 1 and 2 and 3. You notice the following. When the input is 5, VA, for example, is 5, DA is forward. And when the input is 0, the diode is just reverse or it doesn't have enough source to give it 0.7 to conduct. Or off. So we notice from 1, 2, 3, the first 3 cases, that when you have a 5-volt input, the corresponding diode is forward and on. When you have a 0 as input, the corresponding diode is off. So let's write this notice here because we're gonna use it. From 1, 2, 3, we notice that if the input at any diode is 0, the diode was off. And when the input is 5, the diode was on. And in our case here, VA and VB is on. So let's assume that DA and DB both on. If DA is on, so VDA equal to 0.7, which is equal to VA minus V out. Again, look at the circuit. We used this equation many times. So V out equal to VA minus 0.7, 4.3. And now the moment of truth. We can verify this from the second one because VDB is also, since VDB is on, is also 0.7, which is equal to VB minus V out. So from here, V out equal to VB minus 0.7, it will be 4.3 volt. Again, it is same value. So we don't have contradiction like number 2 and number 3. So this is here 4.3 volt. Of course, we didn't calculate the currents in all the, but you can calculate it in a very easy way. Okay, and the resistance here is 1 kilo ohms. I just forgot to put the value, it's 1 kilo ohm. So you can calculate the current in a very easy way. One may say, no, in that case, they were off. They were not on. Okay. You can assume that. You can assume in this case that DA or DB or both are off. And for sure, you will find you have some inconsistency, contradiction, something, a fact that is not, that is incorrect, you know, something that will give you a clue that this assumption is wrong. The only valid assumption here is that VA and VB is right. And how we could guess this from the beginning, we just looked at the 3 previous examples or states, 0, 0, 0, 5, 5, 0, and 5, and of course, we are calculating 5, 5. So from the previous 3 states, we find that when the input is 0, the diode was off. When the input is 5, the diode was on. Okay? So we just completed the table now. We just completed the table. Now it's a time to analyze this table and deduce the kind of application that this circuit represents. Okay? So this is what we're gonna do in the next video. So stay tuned to have more insight about this circuit and what possible applications for it. Okay, thank you very much and have a great day. Bye-bye.